Okay, so today we keep learning about pH effect on the enzymatic kinetics and how the pH affect enzymes kinetic parameters Vmax and Km. So this is a little complicated case where we have free enzyme EH which can be deprotonated or protonated furthermore, and also enzyme substrate complex EHS can be protonated or deprotonated. So we have 1, 2, 3, 4 ionization state which are assumed at equilibrium. And on the line of a buck plot, we can find that we do not have common point on y-axis or x-axis. We have some common point on this plane. I would not expect you to be able to derive rate equations for this case because this is probably too difficult and out of scope. But if I show you just the result, if we plot log Vmax apparent as function of pH, we'll have some optimum point for the maximal value of Vmax apparent. So as we increase pH starting from low pH value, then Vmax start to increase, and then that value reaches a maximum point. Then as we increase pH further above this optimum point, then Vmax value start to decrease again. And this phenomena is contrast to what we have seen previously with other examples. For example, okay, so in this first example, where you have an enzyme which is active in deprotonated state, we have common Vmax value, and this Vmax value is independent of solution pH, while Km value depends on solution pH. And okay, so if I take another example, as you have seen, if protonated enzyme is active, we can see this pattern for Vmax of Km as function of pH, but Vmax value is again independent of solution pH. And as you can see in this case also, Vmax value is independent of pH. But in this new example, Vmax depends on pH value and has a maximum value at some optimum pH. Probably the most complicated case can be shown here. Okay, so this is like non-competitive inhibition mechanism, and as you can see, these protonated or deprotonated or protonated forms of free enzyme can also bind substrate to form ES complex, but they are not active. Okay. And if you try to understand what will happen to the Lineweber plot, then we can see that we have Km value which is independent of solution pH, while Vmax apparent value is affected by solution pH. And this is the kinetic expressions for Vmax apparent and Km apparent, which depends on the proton concentration. Okay. And sometimes we have substrate which can be ionized also. Okay, so this is just one of the model proposed for this case. And as you can see, we have free enzyme which can bind substrate from EHS, and then that go through the normal catalytic cycle of the enzyme to produce product and to recover the free enzyme. And in this case, we'll consider that this EH can be deprotonated to form inactive enzyme. And furthermore, this substrate can be protonated to form non-reactive substrate. Okay, you can probably come up with different mechanisms based on the kinetic result. Okay. So for this case, we'll see what happened to Vmax apparent and Km apparent, and these two ionization constants are for the respective reversible steps. Okay. So we'll start with Vmax, which is K2 times the concentration of enzyme substrate complex, EHS. When we have three constants for the binding step between enzyme and substrate, and for the ionization step for the enzyme, and the ionization step for substrate. And total enzyme concentration is the sum of EH and E negative. Okay. And substrate concentration is the sum of the substrate concentration S and the concentration of protonated substrate SH plus. So V equals K, which is KK or KM times EHS, and you can substitute these two relations into here to come up with this equation. Okay, so I jumped over a little bit more steps between these two equations, but you can try to solve this to find these equations yourself. So we'll set this as K apparent E0 S0. Okay, so K apparent is the K over this value. Okay. So what you can see for K apparent value is that we can again see the bell-shaped curve with the optimum pH point. Okay. So that's it for the pH effect on enzyme kinetics. Okay. Okay. So just before I turn to another subject, just you have to remember that these equations are derived based on this simplified reaction mechanism. Okay, so that's why we do not have here EHS. Okay, we do not have EHS concentration term in here because we used this reaction mechanism as a basis for the derivation of kinetic expression. Okay, okay. So another factor that can affect enzymatic catalysis is pressure. Okay, so for most of the enzymatic catalysis, pressure may not give a strong effect on the kinetic constants. However, for some enzymes which are associated with some dissolved gases such as oxygenases or decarboxylases, where gases O2 or CO2 are associated, the pressure may affect enzymatic catalysis strongly. Another example of the enzymatic catalysis which can be affected by pH is the enzymatic reaction in supercritical CO2. Okay, so the CO2 can become supercritical solution at 31 degrees C and 73.8 bar, which are rather mild conditions, so that enzymatic reactions in supercritical CO2 have been actively studied. Okay, so before I go into the kinetics, I will introduce some thermodynamic equations that include pressure effect. So first we'll start with Gibbs free energy. Okay. Okay. Gibbs free energy depends on temperature and pressure according to this equation, where S is the entropy, V is the volume. Okay. So between state A and B, if we take the difference, then difference in Gibbs free energy is same as negative difference in entropy times dt plus difference in volume times dp. So that d delta g equals negative delta s dt plus delta v dp. Now, if we change pressure, so pressure is not constant. However, if we keep the temperature constant, okay, so that dp is not 0 while dt equals 0. Okay, so this term will disappear, and so d delta g equals delta v dp, and 0 represent the standard state. Okay, and remember that this Gibbs free energy difference is always associated with equilibrium constant K. Okay, so and with this relation, so Gibbs free energy difference is always related to the equilibrium constant by this equation. where K equilibrium is the equilibrium constant, which is the in enzymatic kinetics inverse of Km for the binding step. And R is the gas constant and temperature is T. So as you can see here, d ln d delta G over dt at constant temperature equals delta V, and dg is expressed by this equation, negative RT ln K. So you can put this relation into here to have this equation. And RT is the constant term, so they can be taken out of the differential term. So d ln K over dt, okay, at constant temperature T equals negative delta V 0 over RT, and RT is also constant. Okay, so if we qualitatively discuss the pressure effect on K equilibrium, if delta V has negative value, okay, which means the VB minus VA has negative value, so volume VB is less than volume VA. Then as we increase pH, okay, pH equilibrium constant value increases, and if we have positive delta V0, so that VB0, okay, is larger than VA0, then as we increase pressure P, equilibrium constant value decreases. So we see what equilibrium values we have, or what equilibrium values are included in the enzymatic catalysis. Okay, so we have two equilibrium terms, constants, associated with enzymatic catalysis. Okay, so this is the normal Maclaurin type reaction mechanism for enzyme, and we have one reversible step where Km is associated, and if you write this irreversible step furthermore into these two steps, where first step is the equilibrium step between ES at ground state and ES at transition state, and V term, the new term. So we have actually two equilibrium constants associated with normal enzymatic reactions. Km value, which is 1 over K equilibrium, which is Km, and Km equilibrium constant for the transition step between ground state and transition state. So that we can associate two volume changes, delta V for this bonding step and delta V star for this transition step. Okay, and depending on the signs of delta V and delta V star, the pressure affect enzymatic catalysis differently. Okay, so K2 equals new K equilibrium and K star equilibrium, and K equilibrium is 1 over Km. And you can see that we have formula terms Km and K2. So we can measure Km value and K2 value, okay, experimentally, so that can be measured value. So what we can do is we can measure K2 value and Km value at different pH solution at different pressure values. Okay, and so that d log K2 over dP at constant temperature is equal to d ln K equilibrium star over dP, and which is the same as negative delta V over RT. So if we plot log K2 as function of pressure, then this term will be the same as slope. So for another equilibrium step, if we plot ln 1 over Km versus P, then we have this slope. So if you prepare actually two plots, one log K2 over P and another one log 1 over Km versus P, then you can estimate the volume changes delta V and delta V star. Okay. So let's see what will happen. What have happened for some real experimental result. Okay. So this is one study published in 1988, long before, where they measured Vmax value, which is related with K cat or K2 E0, okay, and Km value at different solution pH pressure, starting from 0.1 megapascal, okay, up to 200 megapascal. So this is almost 1 atm. Okay. So they measured activity of the enzyme at different concentration of substrate under different pressures. And from each line, on the line of a bulk plot, they estimated Vmax value and Km value, and they plotted log Vmax as function of pressure and log Km as function of pressure. Then, as we already have seen in the previous pages, log Vmax over K log Vmax over pressure will give the slope, which is the same as negative delta V star over RT. And the plot between log Km over pressure will give the slope, which is the same as delta V over RT. Okay, so we do not have negative sign here because Km is 1 over K equilibrium for the binding step. So we already know the value of gas constant R and the constant temperature for the experiment, so that from these slopes we can estimate the volume changes delta V star and delta V for the transition step between ground state and transition state and the binding step. Okay, and as you can see, we have probably positive delta V, and here we have very little change in delta V. Okay, if there are some delta V values, then this value will have very small negative value. Okay. And We have another example where the velocity of the reaction, enzymatic reaction, is measured at different P pressure value, and if we plot log, okay, which is actually log V reaction rate as function of pressure P, then we have two straight lines, and these lines are for different substrate for the enzyme alpha chymotrypsin. Okay, so we can also see that delta V depends on the types of substrate. Okay, so we are done with the kinetic effect of different environmental factors such as temperature, pH, and pressure. And the final factor that could affect enzymatic catalysis is salt. Okay. So sometimes we can find microorganisms which can live well in solutions which are saturated with salt, and these bacteria are called halophilic bacteria. And some enzymes which are separated and purified from the halophilic bacteria can be halophilic enzymes, which means enzymes like halogen or salt. So this is one example where reaction rate V and V over S. V is measured as different substrate concentration in different salt solutions. Okay. So as you can see, for this Halobacterium salinarium, for this enzyme dehydrogenase purified from Halobacterium salinarium shows that the salt Na sodium chloride can affect the kinetics. Okay, and I'll just show you some examples to see how salt affect enzymatic catalysis. And this is the experimental result for the catalysis of halophilic protease purified from Halobacterium halobium. And as you can see, as we increase the concentration of salt, sodium chloride, from 0 to the saturation value of about 4 mole, you can see that kcat over km increases. Okay, so as we have stronger salt solution, this enzyme shows higher catalytic power, kcat over km. And if we plot kcat and km separately at different salt concentration, it was found that kcat value was not affected much by the salt. However, major effect is for km value. Okay, this is for km, and this is kcat, and that's kcat over km. Okay, and another example is for the enzyme ribonuclease, and they measured kcat over km value at different salt concentrations. Okay, so you can see that you can as we increase salt solution, kcat over km value decreases. That's because probably this enzyme ribonuclease are just normal enzymes, not halophilic enzymes. Okay, so if you have halophilic enzymes, they show higher catalytic power as increasing salt concentration. However, for the normal enzymes, if you increase the concentration of salt, probably the catalytic power decreases. Okay, so that's the end of this lecture, and also this is the last lecture video for this class. So I'll post you the final exam schedule on class, so you have to keep watching the announcement about the final exam schedule. And final exam will cover all the subject starting from the very first part of the lecture up to this point. Okay, thank you so much for listening and watching my lecture videos. Thank you very much.